In early Bitcoin, paying someone meant typing their IP address. Your computer dialed theirs, asked for a public key, and built a transaction on the spot. It worked? Barely. Today, we trace how a simple cryptographic hash killed that design and gave us modern Bitcoin addresses. To understand why, we need Bitcoin's script model. Every coin is locked by an output script. Think of it as a puzzle. To spend the coin, you provide an input script. The solution. The two scripts run together on a stack, a last in first out list of values. If the final stack top is 1, the spend succeeds. Everything in Bitcoin payments reduces to this: a locking script on the output, an unlocking script on the input, evaluated together. The original payment type is called P2PK, pay to public key. The output script is just 2 items, the receiver's 65-byte public key, followed by the opcode OP checksig. The input script is a single signature. Let's run it. Step 1. Push the signature onto the stack. Step 2. Push the public key on top. Step 3. OP checksig pops both, verifies the signature against the key and the transaction data, and pushes 1 if valid. Stack ends with 1, script passes, coins move. That's the entire mechanism. The public key sits openly in the output, acting as the destination address itself. So how did you share your public key? A 65-byte key is 130 hex characters, impossible to read aloud, painful to type. Satoshi's solution: skip the key entirely. You give out your IP address. When Alice wants to pay you, her node connects to yours. Your node generates a fresh public key on demand and sends it back. Alice builds the P2PK transaction and broadcasts. Bonus feature: every payment used a new key, giving strong privacy by default. The problem is obvious in hindsight. To receive money, you had to be online, reachable, and free of firewalls or NAT routers blocking incoming connections. Miss any of those and payment failed. You couldn't put an IP on a business card, email an invoice, or accept donations while asleep. Bitcoin needed a way to hand out a receiving identity that worked offline, stayed short, and still tied uniquely to your key. The fix starts with cryptographic hashes. A hash function takes any input and produces a fixed size fingerprint. It's deterministic. Same input, same output. One way, you can't reverse it. And collision resistant. Finding 2 inputs with the same output is computationally infeasible. This makes a hash a commitment. Imagine writing an answer, hashing it, and publishing just the hash. Later, you reveal the answer. Anyone reruns the hash and confirms it matches. You commit it without disclosing. Apply this to a public key. Publish the hash now. Reveal the full key only when spending. That's the core idea behind modern addresses. Bitcoin's specific recipe is called hash160. Take the 65-byte public key. K, run it through SHA-256, producing a 32-byte digest. Run that digest through RIPEMD160, producing a 20-byte output. That 20-byte value is the address hash A. Satoshi never explained why he chose 2 different hash functions stacked together. One theory is defense in depth against a weakness in either one. The result is what matters. A 65-byte key compresses to a 20-byte commitment, shrinking the data Alice needs to receive by more than 3 times. This gives us P2PKH, pay to public key hash. The output script has 5 pieces: opdope, op hash 160, the 20-byte commitment, op equal verify, op checksig. The input script has 2, the signature, and the full public key. Let's execute. Push signature. Stack has sig, push pub key. Stack has sig, pub key. opdub duplicates the top. Stack has sig, pub key, pub key. op hash 160 replaces the top copy with its hash. Stack has sig, pub key, hash of pub key. Push the committed 20-byte hash from the output. Stack has sig, pub key, hash of pub key, commitment. op equal verify pops both hashes, aborts if they differ, continues silently if they match. Stack returns to sig, pub key. OP check sig pops the remaining 2, verifies the signature, pushes 1, script passes. A common question: why OP dupe? Because the script needs the public key twice. Hash 160 consumes 1 copy to compare against the commitment, proving the spender knows the right key. But checksig still needs an intact public key to verify the signature. Without DOP, the first operation would destroy the data the second one requires. Every opcode in P2PKH earns its place. Nothing is decorative. Compare the two designs. P2PK puts a 65-byte public key in the output. P2PKH puts a 20-byte hash. To receive, P2PK forces you online and reachable. P2PKH lets you share a hash offline, on paper, in email, printed on a sign. Both support fresh keys per payment for privacy. P2PK is now rare, surviving mainly in old coin-based outputs. P2PKH became the dominant legacy format for over a decade. The key insight: by committing to the public key with a hash, Bitcoin decoupled the act of receiving an address from the act of being available on the network. We've gone from 65 bytes to 20, but 20 raw bytes of hex is still a transcription hazard. 1 wrong character and funds vanish forever. The next step wraps that hash in an error-checked encoding called base 58 check, and later back32. Zoom out and a pattern emerges. Bitcoin evolves by adding commitments, Merkle roots, SegWit, Taproot. Each keeps data compact and reveals detail only when spent.